All right, so we're going to move on then, and we're going to be looking at area between functions. This starts off fairly straightforward, but there's a lot of layers to some of these questions, and it makes getting to the final answer somewhat challenging. We're going to be determining area between multiple functions. We're going to be looking at 2 examples today, and then you'll be able to build off of those examples and do more complicated questions. So what is the area between these 2 curves? The first thing to note is that I'm not telling you from what to what. And just like the example we started off yesterday with, if I just say find the area between 2 curves, or find the area, I guess what I'm telling you is that the area is an enclosed area. If this area that we're asked to find were not enclosed, then when we looked at the graphs, it could be anywhere. And you would need parameters then. You would need to know from this value of x to this value of x. Hopefully it loads. There it is. Yeah, sure. That's what it looks like. If you were to use your mathematical skills, you'd discover there's no x-intercepts, and it happens to intersect at a couple of points. You can see looking at this graph that it intersects at x equals 1/2 and at x equals 4. So what we are trying to determine is that, right? That's what we're trying to determine. And the question is, how can we do that? So I'm going to draw just a rough sketch here. What we have basically is the following situation. We have our linear function. Looks like this. We also have our quadratic function, which looks roughly like this. And the question is, what is this enclosed area? And this gets awfully difficult for you to communicate visually on paper. I know most of you know exactly what needs to be done here. Okay? And I kind of led with this question near the end of yesterday's class. I've got the graphs loaded up here. Sorry, I'm moving a little slow here this afternoon. If that's the area we want to find, just ignore that area for a second and ask yourself, do you have the ability to find that area? Yes, and you could do it with geometry because it's a straight line, it's a trapezoid, but we would do it with calculus. What we would do is find the antiderivative of 1/2 x plus 4 from x equals 1/2 to x equals 4. Okay? And then the next question is, could you find this area? And the answer is, well, yes, you would do the same thing, except your integrand, the thing you anti-differentiate, would be x squared minus 4x plus 6. And I hope it's clear that if you take that red area, this area, and you remove from it this area, what you will be left with is the area of interest. Okay? And we're going to end up coming up with a new rule here that I will introduce you to in a second. But the bottom line is we're going to find the area below the upper function and subtract from it the area below the lower function. The only problem is, where does this begin and where does it end? Well, you only know that it begins at 1/2 and ends at 4 because I showed you that graphically. You have to be able to show this on paper. You have to use your algebra skills here to determine the points of intersection. And these 2 functions will intersect. Is this the function? Thank you. They will intersect when their y coordinates are equal to each other. So this is the equation that you need to solve. You're just finding points of intersection. I'm going to multiply both sides of this by 2. To eliminate the fractions and get 2x squared minus 8x plus 12 equals x plus 8. That looks okay. It's quadratic, so I can zero the equation to proceed. and get 2x squared minus 9x plus 4. Is that right, you guys? It's just, well, I was going to say let's do the discriminant test to see if it's factorable. We know it's factorable because we get integral points of intersection, right? 1/2, not integral, rational, I guess. 1/2 and 4. This is equal to 0. Let's just go ahead and factor it. It's going to be 2x, x. You know, it's interesting because of all the times we've talked about factoring in my classes anyway, I've said with a number like 4, try 2 and 2 first before you try 4 and 1. How many of you see why it's not going to be 2 and 2? How many of you see why it would never be 2 and 2 in this circumstance? Because we already have a 2 in front of the x. If it were 2 and 2, I would have to include a common factor of 2 somewhere, and that can't happen because there isn't one here. So 1 and 4, minus and minus, and you can confirm that that's true by foiling it out, which means the point of intersection is x equals 1/2, and the other point of intersection is x equals 4. Going back to this statement written beside the graph, that if I take, and I run the risk here of making things maybe overly cluttered on the board, but I'm going to give it a shot anyway. You know, the area below the upper function is this. By the way, this is the upper function. It's the one that it forms the top of the area, whereas this is the lower function, the one that forms the bottom of the area. If I take that blue area and subtract not what I wanted to do, and subtract this green area, I hope that you see we're left with the enclosed area, which is what we want to find. So that means that this area will be equal to the integral from 1/2 to 4 of the upper function minus the integral from 1/2 to 4 of the lower function. Can you just double check to see that I've recopied those functions correctly? There, good. Okay, good. So, what are we going to get? This will be 1/4 x squared, and I paused there because I have to think about what the antiderivative of a 1/2 x is. It's not, you know, we've done that x squared turning into 1/3 x cubed a dozen times. So I don't even have to think about it. But this one I had to stop and think. Plus 4x, evaluated from 1/2 to 4, minus, this will be 1/3 x cubed minus 2x squared plus 6x from 1/2 to 4. I'll just double check that and ask you to double check it as well. But I think it looks okay. Now we can go ahead and put the numbers in. Are we in agreement on that line? Okay. We can go ahead and put the numbers in. So we're going to have 1/4 times 4 squared plus 4 times 4 minus, in brackets, 1/4 times 1/2 squared plus 4 times 1/2. Then we're going to have to subtract 1/3 times 4 cubed minus 2 times 4 squared plus 6 times 4. Minus, I hope you're understanding here, we've got minus stuff that's in brackets a lot here. So those brackets are crucial. The same antiderivative at 1/2. This is going to challenge my mental ability this afternoon. And And before I get started on tackling all of these pieces, I better step back and make sure I've transcribed everything properly. The antiderivatives are fine. I put in 4, I put in 1/2, and then I'm subtracting. I think I need technically another set of brackets here. And then I've got 1/3 minus 2 plus 6, those are okay, and 1/2 minus 2 plus 6. Okay, let's see how I do here. I believe this is 20. I'm going to need just a second to work this out. I believe that's 33/16. Thank you. I don't need that set of brackets, but I'm trying to impress on you that that thing is the area below the linear function. Minus (44/3). No, I didn't get it. I want to give it another shot. 24 minus 32 is -8, and I have 64/3 minus minus 8. 64/3 minus 8. 64/3 minus 24/3. It's not 40/3? Oh, what did I say earlier?
44/3.
Oh, thank you. 40/3. It is 40/3. Okay. Yeah, let me give it the old college try. I just have to write part of these numbers down. 1/24. Minus 1/2. 61/24. Wow. Okay. No, 24, 8. Oh, 8. 8 times 40 is 320. 320, how about 259/24? And I'm sorry, but that's where the show ends. I'm not going to try to do that. The common denominator would be 48, I suppose. And I'd go 3 times, no. I'm just going to be wasting everybody's time doing that. And again, I've mentioned this before. Sometimes I just like to do that. I'm doing it to keep my brain sharp. Luckily, though, so what do we get for an answer in simplified form? 343/48. Okay. Luckily, though, we don't have to do all of that. And I know that you kind of maybe get a little upset at this point going, well, if we didn't have to do all that, why do we do all that? Because it's the logical approach to this. And I don't want to get into a proof of why this will work. But up here where we have these two integrals, since they both have the same lower limits and upper limits, rather than integrating each of them and evaluating each of them separately and then subtracting the results, you can subtract the integrands and do one integral. So what we have here is the integral of the upper minus the integral of the lower. We have the integral from a to b of the upper function minus the integral from the same a to b of the lower function. And I'm telling you that this is the integral from a to b of the upper function of x minus the lower function of x. It's not a difficult thing to see when you start to consider what it is you're doing with those numbers. And the reason why that becomes easier is what we're going to end up with when we finally figure out what this is one thing minus another thing. That will be it, because it's a single integral. So we have from 1/2 to 4, 1/2 x plus 4 minus x squared minus 4x plus 6. We can subtract those first and have a lot less to anti-differentiate and a lot less work beyond that point. This is the integral from 1/2 to 4 of negative x squared. I also have a 4x and a half x, which is 9/2 x, I think. We also have a 4 minus a 6. Oh, wow. I mean, let's face it, back here, you had to deal with a quadratic antiderivative, right? But you also had to deal with another linear one, and you had to deal with subtracting them from each other, and each of them are actually differences in their own right. So it's, it's brackets something minus something, n brackets minus brackets something minus something. Here, that's not going to happen. Here, what you're going to have is negative 1/3 x cubed plus 9/4 x squared minus 2x. Anybody want to check my anti-differentiation, make sure it's okay? All right, from 1/2 to 4, okay? So, I mean, there's a lesson here, and the lesson is this. Subtract the upper function minus the lower function first, simplify that, and be as happy as you can be doing this anyway, but you're a lot happier doing it that way than you are doing it this way. Unfortunately, some people do it the top way because it just makes more sense to them. Logically speaking, they understand exactly what's happening. You do start to lose the thread of why this works when you start doing this on the bottom. You're more rule-oriented, but that's okay. You will also notice, and I'm just going to address this now, and then we can finish with the second example. It doesn't matter where the axes are. And the reason for this is, let's just say, well, let's go with this. Let's say that this is a y-coordinate of negative 10. Okay? Would you agree that if I added 20 to each of those functions, the area between them from a to b would still be the same? And both of those functions would then be above the x-axis? Okay. So what I'm going to demonstrate to you is this. I'm claiming that, which is what you're asked to find, or no, I'm claiming that, this, which is what you're asked to find, I'm claiming is the same as this. Which, I mean, it's the same area, right? Well, if I simplify these, I'm going to get 20 minus 20. I'm back at the beginning. So it doesn't matter where they are. And the other thing I want to briefly talk about, although I'm not going to discuss why this is the case, we have been pretty much confining ourselves most of the time to positive A's and B's. It doesn't have to be. This stuff can be way over here. It can be way over on the left-hand side in quadrants. It can be in any quadrant, left, right, up, down. It will always work. So let's do the final example. I guess before I do, any questions with this idea of subtracting the upper function minus the lower function first and doing one integral? It's what you want to try to do. So, and this I believe is in your notes. Right? This is what we did to solve the first example today, and then this is what I set up, and we didn't finish it, but I said that will work as well. The key, though, is to make your job easier, make sure you simplify this. All right, let's try the final example. Find the area between the curve sine of x and cos of 2x from negative pi over 2 to 5 pi over 6. Because of time issues, I'm not going to stand up here and go over how we graph these on paper. That's just going to take forever. You should know how to do it, but let's graph them on our calculator. Y equals sine of x. And y is equal to cos of 2x. I need to go zoom trig. And it doesn't matter because we're not really going to be doing any calculations with the angles on our calculator, but I do want to be in radians just because that's what we usually do. Zoom 7. Don't know why I did that. There it is. Okay. So this is sine of x, and this is cos of 2x. So sine of x is the one that has a greater period. It's stretched out more horizontally. And this is scaled from 0 to 2 pi, essentially. Negative pi over 2 is here. 5 pi over 6 is here. We need to find out the points of intersection of these two functions. And this I'm not going to skimp on. We need to take sine of x equals cos of 2x and solve this equation algebraically. It's going to be done by replacing cos of 2x with an equivalent trigonometric expression that is going to allow us to solve the resulting equation. And you can replace cos of 2x with cos squared of x minus sine squared of x, but that's a bad move because then you have cosines and sines. You can replace cos of 2x with, am I right, 2 cos squared x minus 1, but that's a bad move as well because then you're going to have a mixture of sines and cosines. You're going to replace it. The wisest move is to replace it with 1 minus 2 sine squared x. We can zero this equation, 2 sine squared of x plus sine of x minus 1 equals 0. Some pretty straightforward trigonometric quadratic factoring. There was a time in your high school career where if you heard somebody say straightforward trigonometric quadratic, your head might have popped off. But this is pretty straightforward. I think I'm okay there. Which means sine of x is equal to 1/2. And sine of x is equal to -1. -1 is here, which of course is negative pi over 2, right? That's where they intersect and where the boundary starts. So negative pi over 2 is a point of intersection on the graph. Sine of x is 1/2 here and here. Well, that's pi over 6. And 5 pi over 6. So what we have demonstrated is that this is x equals negative pi over 2. This is x equals 5 pi over 6. And this is pi over 6, which is a nice, I wish we had more time in Math 30-1 to make connections between the unit circle and graphs. It's a really nice visualization of what we just saw in the unit circle. In this region here, this area that we are trying to determine the value of, the upper function is sine of x. Nope. The upper function is cosine of 2x, and the lower is sine of x. Let me highlight sine of x for you. Sine of x is this one. So in that region, that little teardrop shape, the upper is cosine of 2x and the lower is sine of x, whereas in this region, the upper is sine of x and the lower becomes cos of 2x. That means that this area, this combined area, is going to be equal to the integral from negative pi over 2 to pi over 6 of the upper minus the lower plus the second area. I can very easily clutter this diagram too much. This is the first area. This is the second area. Plus the integral from pi over 6 to 5 pi over 6 of the upper, which is now sine x, minus the lower, which is cos of 2x dx. I mean, again, I want to say something to you that I said earlier, or I alluded to earlier if I didn't say it. This is perhaps the most important part. Not only because if you don't get this right, you're not going to get to the answer, but this is the calculus and anti-differentiating. But beyond that, it's just a bunch of grunt work. Any questions with setting that up? In fact, I have seen exam questions in university that are multiple choice. And by the way, multiple choice questions in university sometimes have A through F. And some of the choices are like A has something and B has something and C has something and D has something. And then E says A and B but not C and D, stuff like that, okay? But I've seen multiple choice questions where it's what is the area between these functions? And this is the answer. Right? That's not where we want to stop here, but that would be the answer. Okay, let's do this. I can tell you're all excited to get this done. The antiderivative of cos of 2x is 1/2 sine of 2x. Just give some thought to why the antiderivative of cos of 2x is 1/2 sine of 2x. And the thought that should be happening is, what do I get if I differentiate 1/2 sine of 2x? Well, I get cos of 2x, because I get 1/2 cos of 2x times 2. The antiderivative of sine x is negative cos x, so the antiderivative of negative sine is positive cos x from negative pi over 2 to pi over 6. Now, luckily, cosine of pi over 2 is 0, so things are going to get a little simpler. And then here, we're going to have cos of x. No, we're not. We're going to have negative cos of x minus 1/2 sine of 2x. Boy, you know, from pi over 6 to 5 pi over 6. These sines and cosines and the positives and negatives and moving forward with differentiation and backwards with anti-differentiation is tricky. Even now, I feel the need to differentiate what I just wrote to make sure I get what's above. The derivative of negative cos is positive sine. That's good. The derivative of a sine that's negative will still be negative cos. It's okay. Now we're doing substitution and the unit circle. Any questions to this point? Right? So we are going to have 1/2 times sine of 2 times pi over 6 plus cos of pi over 6 minus 1/2 times sine of negative pi over 2 times 2 plus cos of negative pi over 2, and I'm going to just step back and look at that. I put in pi over 6 there, and I put in negative pi over 2 there. That's good. Plus, boy, you know, I would be tempted here, everybody, to peel that negative out and put it outside of the brackets, but I'm not going to. Cos, negative cos, this time we're looking at 5 pi over 6 minus 1/2 times sine of 2 times 5 pi over 6 minus negative cos of pi over 6 minus 1/2 of sine. You can go a little crazy doing this. At least I can. There's a lot going on here. Of 2 times pi over 6. And now I need to step back and look at everything. I just want to make sure. Pi over 2. Here I've got negative cos and 1/2 sine, negative cos and 1/2 sine, 5 pi over 6, 5 pi over 6, and pi over 6. Okay. This 2 times pi over 6 is pi over 3. Sine of pi over 3 is root 3 over 2. Times that 1/2. This is root 3 over 4. Plus cos of pi over 6 is root 3 over 2. Minus 2 times negative pi over 2 is negative pi. Sine of negative pi is 0. We caught a break. Finally. Cosine, we got another break. Don't try to read too much into why we're getting some zeros here and how that works. Cosine of negative pi over 2 is 0. We really got lucky there. Plus negative cos of 5 pi over 6. Cosine of 5 pi over 6 is negative root 3 over 2 times the negative in front is root 3 over 2 plus, minus sine of 2 times 5 pi over 6. 2 times 5 pi over 6 is 5 pi over 3. 1, 2, 3, 4, 5 pi over 3. Where am I? Sine of 5 pi over 3 is negative root 3 over 2 times negative 1/2 is positive root 3 over 4. And I need to run that through my head again just to make sure. 2 times 5 pi over 6 is 5 pi over 3, which is in this location on the unit circle. The y-coordinate there is negative root 3 over 2 times a negative 1/2 will make it positive root 3 over 4. I think we're good there. I'm wondering if the rest of this is going to be zeros. No, it won't be. Minus cos of pi over 6 is root 3 over 2. But it's negative cos, so it's negative root 3 over 2. The last term, 2 times pi over 6 is pi over 3. Sine of pi over 3 is root 3 over 2. We're subtracting it, so it's negative, and it will be root 3 over 4. Boy, we've got a lot of root 3 over 2s and root 3 over 4s everywhere. In fact, we can get the answer very quickly here. We have 1 root 3 over 4 plus another root 3 over 4 plus another root 3 over 4. We have 3 root 3 over 4s. We have a root 3 over 2 plus a root 3 over 2 plus another root 3 over 2. And I would say we can end there. If you want to multiply the top and the bottom of that second term by 2 so that we can get a common denominator of 4, well, I guess we can do that. You'll have 3 root 3 plus 6 root 3 all over 4. I've multiplied the top and the bottom here by 2. I guess that bears fruit, leads us somewhere, 9 root 3 over 4. That was a workout, that one. If you wanted to check it on your calculator, we haven't talked about this yet, and I think we can squeeze in just a little bit of time here. I think we will most likely be doing more area practice tomorrow, okay? Because there's other types of questions. If you wanted to check this, then you could do the following. So one of these had sine above cosine. Can you tell me the one where sine was on the top, was that the first little area or was it the bigger area? It was the bigger. So that was from pi over 6 to 5 pi over 6. So what I could do is subtract them here and do my calculate from pi over 6 to 5 pi over 6. And if I've entered this right, it will be a nice area sandwiched against the x-axis. It's going to be this area here. By the way, my graphing calculator gets a little pointy there. It should be smooth. So I'm going from pi over 6, pi over 6 to 5 pi over 6. And I'm just going to grab that. Then I could, and I'll show you a shortcut here, then I could repeat the process, but do cos of 2x minus sine of x. And now we're going to go from negative pi over 2 to pi over 6. I think it's interesting, and I think many of you will find it interesting as well, that we're getting areas that are against the x-axis. And I could take these two numbers and add them together. Has anybody worked out what 9 root 3 over 4 is? What do you got? 3.89. Add those two together. I mean, you don't have to do it that way. You could do this. Right? If you just wanted to know an answer, you could just fold anything negative above the x-axis and do the absolute value area from negative pi over 2 to, was it 5? Yeah, it was 5 pi over 6. And that should be the answer, right? All right. On page 462, question number 1 has a boatload of problems. There are some very, very elementary, basic types of questions. Well, not very, very, but there are some beginner questions. There are some intermediate questions, and there are some certainly challenging questions. By the way, because nobody asked, but I'm going to mention it anyway, these integrals that we were working on here, you cannot combine these two integrals. Why can you not combine these two integrals? They're different boundaries, right? They're different lower and upper limits. So practice some of those for tomorrow. We'll start off tomorrow's class by me going over some questions if you have them. I hope you do, because I think you learn just as much from me going over questions for you as you do trying them on your own. But then we will continue to work on this tomorrow, I think. And I'll continue to show you other twists and turns you might encounter.